My name is Nicholas Stegg, and the biomedical technology I designed is a forefoot elevating insole for Achilles tendinopathy. This insole is intended to support Achilles tendon conditioning through a controlled change in foot posture. The idea was to create something wearable, low cost, and easy to integrate into normal footwear. Achilles tendinopathy is a common condition, especially in active populations. It affects 52% of long distance runners, 24% of athletes, and 6% of the general population. The condition causes pain and stiffness in the back of the heel and lower leg, especially during movement or after periods of rest. Because of that, basic activities like walking, climbing stairs, exercising, and even pushing off the foot can become more difficult and extremely uncomfortable. Over time, it can reduce tendon function and overall activity tolerance, which can impact mobility and quality of life. One issue with current approaches is that many of them focus more on symptom relief than on gradual tendon conditioning and long-term treatment. In contrast, my design is intended to address the underlying mechanical issue by promoting repeated low-level tendon engagement rather than only reducing discomfort. There is a need for a simple wearable design that encourages controlled tendon loading. Another challenge is that many rehabilitation approaches can be time-intensive, uncomfortable, or hard to maintain consistently in daily life. Because of that, adherence can drop off even when the rehabilitation plan itself is effective. My overall design goals are to create an insole that ultimately promotes forefoot elevation. I want to encourage flexion and gradual tendon engagement over time while keeping the design simple, wearable, and easy to integrate into a shoe. The main goal is to provide a passive rehabilitation aid that can be used during normal daily activity without requiring complex equipment or supervision. My proposed solution is a shoe insole that gradually raises the user's forefoot to an elevation height of 11 millimeters. The idea is that the slight elevation changes the foot's contact geometry and creates a more consistent forefoot elevated position during wear. In this design, the insole acts as a passive rehabilitation aid, meaning it does not require active adjustments, electronics, or any complex equipment. This posture change is intended to promote flexion and repeated low-level tendon engagement, which aligns with the exercise-based loading strategies used in a lot of Achilles tendon rehabilitation literature. And as you can see on the right here is the design of my invention with an 11 millimeter forefoot extension, and that's gradual over 55% of the insole. For the raised forefoot region and elevation height, I based the design on literature showing that forefoot wedge components can meaningfully change foot mechanics, and that those changes can be dose dependent. Studies on forefoot wedges during jogging showed measurable changes in forefoot kinematics, center of pressure path, and pressure distribution as wedge magnitude changed. I did not find literature that specifically prescribes raising the forefoot 11 millimeters for Achilles rehabilitation, so I treated those dimensions as a prototype level engineering decision. I chose them to create a noticeable but still wearable forefoot elevated posture, rather than extreme geometry that would be harder to tolerate in a shoe. For the actual design material, the literature pointed me toward EVA as the strongest choice for a prototype insole. EVA is widely used in orthotic and insole design, and research shows it can reduce plantar pressure effectively. Studies comparing insole materials also found that softer materials, including soft EVA, generally offloaded pressure better than more rigid options in several plantar regions. Based on that, my conclusion was that EVA gave the best balance between cushioning, common use in insoles, and the ability to fabricate the design in a realistic way. I consider comfort as one of the most important design requirements because even a mechanically effective insole will fail if people do not want to wear it consistently. The comfort literature on foot orthoses suggests that contour and fit can matter as much as, or even more than, hardness alone. So instead of thinking only about how soft the material was, I also considered how the raised region would transition into the rest of the insole. That is why the goal was not just elevation, but a shape that would feel more natural under the foot during walking. I also had to consider stability, because if the insert feels unstable inside the shoe, it would not be practical for everyday use. Research shows that orthoses can alter lower limb biomechanics and, in some cases, improve balance-related measures, which means geometry and support really do matter. Because of that, I wanted a design that held its shape under load instead of collapsing too easily. That is another reason EVA made sense here. It can provide some cushioning, but still enough structure to maintain the intended forefoot elevated position better than a very soft foam alone. The prototype was built mainly to test fit and feasibility. At this stage, the goal was not to claim full clinical proof, but to show that the concept could actually be made, inserted into a shoe, and worn in a way that produced the intended forefoot elevated posture. It also gave me a way to think about practical factors like whether the insole fit inside footwear, whether the geometry felt too aggressive or tolerable, and whether the material seemed appropriate for future development. I created the prototype through manual dimensional design, where I took a piece of lightweight fiberboard as substitute for EVA and measured my foot dimensions and cut accordingly. I then used superglue, a ruler, and extra material to add the gradual elevation. This process required some iterative refinement, as it took a while to find a balance between the elevation gradient and comfort. In terms of results, the prototype fit inside the shoe as intended and was fully functional. It achieved the target geometry, including the forefoot coverage and the 11mm elevation. Users reported that the forefoot elevation was noticeable, but only minimally invasive, which suggests that the posture change was present without being overly aggressive. The design also remained stable during walking and standing. Overall, the initial feedback suggests that the concept is feasible as a conditioning-oriented insole design. In conclusion, a forefoot elevating insole was successfully designed as a conditioning concept for the Achilles tendon. The geometry offers a simple mechanical approach to altering foot posture without requiring a complicated system. The prototype also demonstrated that the concept is physically feasible and can be integrated into a wearable insole form. Moving forward, user studies and clinical validation would still be needed to evaluate biomechanical effects, comfort, and long-term rehabilitation potential. Here are all the references I used. Thank you for listening.